Thanks everyone for joining. So today, as Deepthi had mentioned, we're going to be talking about interactive weak supervision for NLP tasks. Um, so kind of uh, by way of agenda, we're going to go through some foundational things. What even is weak supervision? How should I reason about it? All the way into like evaluating results and using some clever techniques to help generate signal for use in weak supervision. For use in weak supervision. Um, so we'll kind of like take a broad survey of several different aspects of weekly supervised learning, but just know that uh, this is certainly not comprehensive. Um, there's a lot more, and I'll kind of hint at various aspects where you can go even deeper throughout the rest of this talk. As Deepthi had mentioned, if you have any questions as we go through, please feel free to ask them in the questions section. I'll be happy to take a look kind of as we go through. Um, but anyway, let's start talking a little bit about weak supervision. I think the first obvious question is, what even is weak supervision? Why should I care about it? So let me sort of like set this hypothetical stage for us. Let's imagine that we're tasked with building uh, some set of models. Let's say that we're given a task by the business to classify such and such data, and the business doesn't have any labeled training data for us. And let's say that it might take quite a while, or it might be very expensive for us to get that training data. Maybe it requires deep subject matter expertise. Maybe it requires doctors, for instance, to weigh in and actually say, oh, this is X or this is Y. All of a sudden, because it'll take so long or it'll be so expensive to acquire that training data, we might want to explore other avenues for generating that training data. So weak supervision is one of these avenues. And the whole idea behind weak supervision is that you're able to take large quantities of independent noisy signal. We'll talk about that in a little bit, and sort of combine them together to produce what are essentially probabilistic labels. Now, weak supervision is not the only way to go about largely automating the process of labeling data. You could do things like um, active learning, for instance, or you could even use transfer learning if you wanted to just label a very small amount of data and train a model that actually performs reasonably well. Each of these techniques have different trade-offs. So weak supervision is not like the be-all end-all, but it's certainly a very interesting technique that is worth sort of having in your back pocket. Um, Now, an obvious question here is like, why not hand label, right? Why not just eat the cost and go through the process of hand labeling? Surely that will be, uh, you know, higher quality and so on. Um, and I'm not going to sort of go too deep into this, but hand labeling has several issues. The biggest issue, and we'll kind of touch on this later on in the webinar, is frankly, if you require hand labels or if you require labels at all that are not inherent in your data, um, interestingly, you don't actually have ground truth. And I know that oftentimes people like to use the term ground truth to describe things that have been evaluated by humans. But in fact, as I'm sure we all know, people can make mistakes. A lot of the time, people will accidentally apply a label that they didn't mean to. Maybe they did a typo and they didn't go back and correct it, or maybe they're tired, or maybe they weren't really paying attention. Whatever the case may be, there's room for error in hand labeling. And that's not to say that weak supervision or any of these like automated techniques will inherently produce perfect labels, but the goal here is really to have an iterative process and one that you can reason about. And one of the other issues of hand labeling is that uh, the labels themselves are opaque. You can't really introspect and figure out why someone said this is X instead of Y. And this is problematic, especially when you want to use that data for downstream modeling processes. You have to be able to trust your upstream sources. So we'll see some of this sort of manifest as we go through. Our sort of our approach to this is that you should have a variety of different techniques backing your labeling process. So hand labeling is an important and invaluable part of it, but it shouldn't be the only technique that you're employing here. You should use it sparingly and use it intelligently. And we'll talk about exactly when you should use it here. And finally, let's talk a little bit about synthetic data generation. As I sort of hinted at before, there is no one-size-fits-all machine learning technique to solve all labeling problems. Weak supervision is really nice when you can discreetly define domain expertise. So a good example of this is like in the medical field or in the legal field or in the financial services field and so on. In other domains and other use cases, it might be a little bit more difficult to define that domain expertise so discreetly, in which case you might actually want to generate a large quantity of training data to then put into a synthetic data generation algorithm, which will then produce new sort of data elements for you to train on. But again, there are several trade-offs there. You know, as I mentioned, you have to have a large quantity of labeled data up front before those algorithms are able to sort of really produce the same type of distribution that you expect in your actual data and so on. So again, no one-size-fits-all ML technique, so I'm couching this pretty hard, but weak supervision is a new and very promising set of techniques, which everyone should at least be aware of, and if not, have in your back pocket or in your data science toolbox. So let's talk a little bit about some very specific weak supervision concepts. Now, just note that we're not going to be using any weakly supervised like libraries here. We're going to be doing everything from scratch. And I want to just make sure that everyone is getting a deep intuition for weak supervision and how it's used and what we can do to sort of help make that process easier. So we're going to focus on kind of three key figures as we go through this process. The first is what we call a base rate distribution. And fundamentally, all that really is in Bayesian terms, it's a class level prior. We want to know, out of my entire data set, how often does the class that I'm looking for show up? Pretty simple. And again, we'll dig a little bit deeper into that in a second. The second is a probabilistic confusion index. And once again, we'll take a look at that in more detail in a little bit, but just to give you kind of a pre-read, confusion matrices, which are standard tools that most data sets or most data scientists are familiar with, they don't actually work very well with probabilistically labeled data. One of the issues there is that most confusion matrices assume that your data is categorically labeled. So it's either a 0 or a 1 for a particular class, and you kind of line up the boxes. The moment your label is not just a 0 or a 1, the moment it starts becoming like 0 to 100, it starts becoming more complicated to put that into like a matrix form. You don't want to be looking at like a 100 by 100 matrix. So giving it a different treatment is actually kind of important. And finally, we want to talk about the label distribution. We want to see how our labels are being distributed through the rest of the data set. So we have a chart for that, and it gives some insight into what sort of class separation we have, where we could focus our time and effort and that sort of thing. But anyway, without further ado, let's sort of load up our data set. So first thing here is I have this data set that I got from Kaggle, and we'll just load that up. And as you can see, it's basically medical notes. So we have 4 columns here. We've got a description, we have a medical specialty, we have a sample name, we have a transcription. What we're going to be doing is we're going to just, as an artificial sort of test here, we're going to be trying to replicate this medical specialty column. And more specifically, we're going to try and look for any row that has something to do with surgery. So very simply, we're going to like look at these rows and see if it says the word surgery here, then we're going to consider it as like quote unquote ground truth for our experiment here. Now, before I dig super deep into that, I see that we have a couple questions. Okay, I'm glad the audio issue got resolved. From Yuri Omar, what about if you have labels, but the labels are known to be very noisy? For example, when users are most likely to group items in one kitchen sink label, can weak supervision help? The answer is absolutely yes. Noisy signal can take many different forms. Previously hand-labeled things can also be used as noisy labels. Now, obviously, the devil's in the details here. We're going to have to sort of dig in and figure out, okay, how do we separate the things that should be part of the label versus things that shouldn't. And this is where having the label itself plus having some heuristics or some other like subject matter expertise that's been discretely defined and encoded could be helpful. But short answer is yes, absolutely. Weak supervision can and should be used in situations like that. Now, is there, I guess, Deepthi, do I mark this as answered somehow, or do I just kind of keep going?
That's okay. You could keep going.
Okay.
I'll take care of it.
Awesome. Thanks, Deepthi. Great. So as I mentioned, we have this data set here. We're basically going to try and recreate one of these labels. The first thing that we're going to do is we're going to simulate a process of hand labeling. Now, mechanically, obviously, we don't really have a way to hand label here, but what we can do is we can say, I want to hand label 250 rows, and I just want to go and see if the row says surgery, and if it does, I'm going to mark that as hand labeled. So we'll run that. And easy, we'll just say anything that doesn't have the word surgery in it is a 0. Everything that does has a 1. And this is two things. So the first is we want to learn some very basic statistical information. So we want to learn how often does this class actually show up in my data set. So again, we're evaluating a base rate. And the second is we're creating a very small validation set. So when you're building these types of systems, what you have to do is make sure that your system as a whole is able to respect class balance, because most data sets are not just like artificially balanced. So this is like the first source of signal that we want to take a look at. And very simply, the intuition for a base rate is just like take the total number of things I looked at and divide, or really just take the total number of things I marked as part of the class and divide by the total things that I looked at. So here we can see that about 24% of our data set is part of this class. Just again, the intuition here is like, imagine I have a deck of cards and I shuffle them up and I pull one off the top and I say, okay, what is this? Is this surgery related or is it not? And you say, no, that's not surgery related. So far, 0 out of 1 things happen to be surgery related. So theoretically, 0% of the things in my hand are surgery related. But we obviously know that's not statistically significant. So I'll pull another one off the top and I'll show it to you. You say, oh yeah, that one is surgery related. So suddenly it becomes 50% likely. And we do it again. And then you say, no, that's not surgery related. So now it's 33%. And you sort of keep going until eventually you converge on a relatively stable number. And in this case, it happens to be 0.24. But now the question is, okay, I keep saying the word distribution, but we just calculated a scalar value here. Where exactly does the distribution come from? And the important thing to recognize is the only way we can actually know the true base rate is if we go through the entire data set and label things one by one. That's the only way. But obviously, we're not going to do that because that would defeat the entire purpose of doing things like weak supervision to label the rest of our data. So instead, what we do is we say that there's going to be some amount of noise around the calculation that we just did. The question is how much noise. So, I kind of wrote up a little experiment here just to show how you can reason about it. But essentially, what we want to say is that given a uniform prior, if we sort of project that over the base rate, we end up with a distribution that kind of looks like this, where it's centered around 0.24. But in fact, we know that the base rate could be as high as, let's say, 0.3, 0.35, or a little bit lower than 0.2, right? So theoretically, the real base rate could be anywhere in this area. Now, as I go through, if I were to label more and more, I would expect that this base rate would narrow in a little bit more. This probability distribution would get a little bit tighter. And just to demonstrate that, we have this little like notebook widget here where as the number of samples increase, you can see how distribution gets tighter and tighter. But interestingly, the closer your base rate is to like 50%, the more samples you need in order to get a really tight distribution. So let me show what that looks like. Let's say that our probability our base rate is very, very small. Let's say like our classes are wildly imbalanced, that my class only shows up 2% of the time. As I increase the number of samples, the base rate distribution gets really, really tight, really, really fast. However, at the same number of hand labels, the closer I get to 50%, the wider that distribution gets. So interestingly, in order to increase the amount of confidence we have in our probability distribution, the closer my base rate is to 50%, the more hand labels I need. And you can see this also on the extreme, like, extreme skew on the positive side. So as I go even further to the right, the distribution gets tighter and tighter at the same number of hand labels. So just like an interesting thing to note here, as you're calculating these base rates, you have to sort of evaluate and see how close to a balanced data set do you have. And if you are really close to 50%, you might need to do a fair amount of hand labeling before you calibrate a really, really nice base rate. So let's say that we have our base rate well calibrated. Let's say that we're happy with our like 0.24 calculation here. We have really our first source of statistical signal. Now we want to introduce some domain level sort of signal. So as an example, a doctor might stand here and say, okay, if I see the word anesthesia somewhere in the notes, then I know that that person had surgery. It's pretty straightforward. So we could imagine that we write a simple regex. If the notes contain the word anesthesia, then mark it as likely surgery. So this is what is known in weakly supervised terms as a labeling function. At Watchful, we call it a hinter. These are relatively interchangeable terms. However, I will say that depending on the type of weak supervision you do, labeling functions oftentimes actually have three possible outputs: a yes, a no, or an abstention. For our purposes, we actually just disregard abstentions because we find that we can statistically infer noise and signal even with just like yeses and nos. So hence why we call it a hinter instead of a labeling function. It's worth having the distinction between a trinary output and a binary output. So for the sake of like this demonstration, we're going to be focused on hinter implementations, which is simply like a binary output. It's either going to be a yes or a no given a particular input. So what we're going to do is we're simply going to check how many rows contain the term of interest, anesthesia. So if we run that, we can see that, I mean, a fair amount, 1,319 total rows. And what we want to do is mark those rows as containing the word anesthesia. So we throw that into a new column, H1. And then what we're going to do is we're going to calculate a probability relative to this. So what we're going to do here is we're going to say if something contains the word anesthesia, it's very likely to be surgery related. Note, it's not a rule. It's not 100%. This is absolutely going to be surgery related, but we feel pretty strongly that if the word anesthesia shows up, it is very likely that that person had surgery. So we're going to pick a very high number for our weight or our expectation, or if you're a Bayesian, this is a prior at the level of a feature. Our feature is, does it contain the word anesthesia? And our prior is just whatever we decide as kind of like the impact that particular feature should have in our probability calculation downstream. So we're going to say 0.95. And we iterate over our rows and we calculate a probability, which is simply, we take the base rate, we add this little weight here, and we average. And that's it. This is the world's simplest label model. So we do that, and we take a look at what our probabilistic labels look like, and we can see it's basically two buckets, which makes good sense. Either it matches the hinter or it doesn't. If it doesn't match the hinter, then we expect it to just be sitting at the base rate. If it does match the hinter, then we expect it to be sitting at the base rate plus the weight divided by 2. Easy. But now we might want to actually see how our, quote unquote model is actually performing. So we hand labeled a whole bunch of data at the very beginning. Now I want to see, okay, of the things that I said or our data said are actually surgery related, how many of those are actually being correctly classified as surgery? So we can just run this, and this is what I called a confusion index before. So the way to read this, I'll zoom in so it's a little bit easier to see. So this chart indicates things that have been hand labeled positively for the class surgery. The Y is the number of rows that were hand labeled positively. And the X-axis is the probabilistic label, so that calculation we just ran. The further right you go, the more likely the system believes that these are surgery related. The further left, the less likely. So for this particular chart, what I want to see is that all of these bars go all the way to the right. And here, again, we have exactly the opposite. We have things that have been hand labeled not surgery. And here, I'd want all of these bars to go all the way to the left. Now, we can see that there's certainly a right skew here and a left skew here, but we're still hovering like sub 60% on these probabilities. So I do want to boost these for sure. And similarly here, we're still hovering at the base rate. So I want to push this more to the left. Now I want to pause and I'll take a couple questions here. What is base rate? So I explained this earlier, but base rate is simply out of 100% of my data, what percent of it is actually part of my class. So in this case, we're looking for things that are surgery related, and based on 250 hand labels that we did, we estimate that about 24% of the data set is surgery related. So that's what we formally call the base rate, or again, in Bayesian terms, this is a prior at the level of a class. And then Omer asked, is there a link for the notebook? Yes, there is. I'll go ahead and I think it'll be distributed after the webinar itself. But yeah, it's all public, so I'll send that along. Anyway, feel free to just keep asking questions as we go through. Anyway, this is sort of like the confusion index that I mentioned will indicate how good of a job we're doing labeling this data. And just to sort of like give everyone additional intuition, let's talk a little bit about what happens if we had no hinters, if we had, like, we hadn't created that anesthesia sort of heuristic. Well, we would expect all of these bars to just be at this 24-25% line. Because the intuition here is that if the only thing we know is that 24% of my data set is surgery related, then no matter what, everything in my deck, everything in my data set will have a 24% likelihood of being surgery related if we know nothing else about it. So what we're trying to do here is introduce additional information so that we can skew away from the base rate probability. So that's functionally all we're doing here. Now, moving forward, let's talk a little bit about the label distribution plot. So this is obviously looking at the things that have been hand labeled, but that's only 250 rows. What I want to do is I want to see what my distribution looks like throughout the rest of my data set. And obviously it looks, very bimodal. Why? Because, well, things either match my hinter or they don't. And if they do, then obviously they have a boosted probability. If they don't, then the probability is just going to be at the base rate, because we have like the world's dumbest model. It's just averaging. We'll do something more intelligent in a little bit, but this is just to sort of build up that intuition. So this sort of makes sense relative to what we've been doing. Now, the obvious next step is let's create a couple more hinters, right? So we'll repeat the same process we did earlier, where instead of looking for anesthesia, we might say if the word blade shows up, very likely surgery related, or at least I hope. So once again, we set a very high probability here. And in our case, we happen to choose exactly the same probability. And instead of averaging with the base rate, now we're averaging with the previous probability. So P1 is either going to be this or this. In our case, it'll either be the base rate because no hinter matched it, or it'll be the base rate plus 0.95 divided by 2. So kind of simple. So we'll run that. And then, once again, we'll plot. And now we can see that it's trimodal, which makes good sense. It either matched, like a row either matched no hinters or just one hinter, and both hinters happen to share exactly the same probability. So, or the same prior. So as a result, they all kind of get stacked in this one place. Or they matched two hinters at the same time, in which case it'll have an even higher probability. So you can see once again in this chart, we're right skewed overall, and here we're left skewed, which is good, but still not perfect because we're still only hitting like 0.75. Like right now, these rows only have like a 75% likelihood of being surgery related. So I do want more signal. So we can just keep going. You know, like once again, we have the label distribution plot, which shows us, you know, once again, we're trimodal. We'll do this again with another hinter called sponge. We can just kind of like keep iterating this way. We can see that we can make incremental progress. Like there are going to be some things that have all four hinters or all three hinters or however many we've created so far matching this particular row or these sets of rows. There will be some that had no hinters match them. So obviously they're going to remain at the base rate and so on. So there are a couple of things that we've done. Number one, we can see that in our positive, in the things that we have hand labeled positively for surgery, those rows are moving more and more to the right, which is exactly what we want. We want the system to be predicting the same way that we've been hand labeling, right? And similarly here, we want a very strong left skew. We want the things that have been hand labeled as not surgery to be correctly predicted as not surgery. However, we can also see that this is a very unintelligent process. There's nothing more than just heuristics matching, and there's, you know, we get like basically this finite floor at the base rate. Like there's a lot of additional things we could do here to make this a little bit nicer. So this is where we bring in kind of a heavier duty model. So in our case here, we're going to learn a generative model for probabilistic labels. So once again, instead of manually going through and creating those hinters one by one, I've collected them here in just two lists. So we have anesthesia, blade, and sponge. And just for the sake of demonstrating, we're also going to create negative hinters. So these are things that are positively indicative of someone who has had surgery. These are things that are negatively indicative of someone who has had surgery. And the intuition for this is, if you look back here, we had to create a prior for each of these features. And in the positive case, they happen to be really, really high, you know, 0.95, let's say. But in the world where you want to create negative hinters, well, you would just create hinters with a very, very low expectation, a very, very low prior. You know, and formally, it's just a prior that has a lower probability than the base rate. So anything under 0.24, we would consider negative or like downward pressure in this case. But here we're going to simply learn a generative model, and I say simply because we're actually just going to use like an sklearn naive Bayes model. But here we're going to create our two lists of positive and negative hinters, and then we're going to just say, okay, for every hinter in positive hinters, if it contains that hinter, then I want to know, and if it contains the negative hinter, I want to know. We just inverse those values. And then we do some sort of like splitting into training and validation sets. And then we're going to train simply a Bernoulli naive Bayes algorithm, which is simply a binary naive Bayes algorithm. We're going to feed it class priors, and it's simply like we know that the data set for our purposes are essentially split into two. The first set are the things that are very likely part of the class, so meaning the base rate. And then 1 minus a base rate is everything that is likely not part of the class. So kind of straightforward here. We'll create that. And then what we're going to do with this trained model is we're actually going to run the same probabilistic prediction on our validation data set and try and visualize what happened with the hand labels. So here you can see that everything got boosted more to the right, kind of unilaterally. Again, it's still very like trimodal, interestingly. But you can see that like, okay, we've got a bunch of things that are actually nearing 100% likelihood. We've got some things that are kind of close, like 80%, let's say. But then the rest of the data set appears to just be hanging out like a little bit north of 50%, which is not really what we want. Like, especially here, we don't want these values, while it's technically left skewed, we don't want the peak of this chart to be so far to the right. What this means is that all of these rows that were actually hand labeled as not surgery currently have a greater than 50% likelihood of being surgery, according to our probabilistic model here, which we know should not be happening. Now, if we plot the label distribution plot, you can see that this is not, this is not specific to the things that we've hand labeled. This is actually across the entire data set. The entire data set has a giant spike, very close to like, let's say 50%, maybe a little bit north of that. Then we have a couple other bumps a little bit further to the right. So this tells us a couple things. First of all, there is an improvement here, at least in the positive aspect. Like the things that are surgery related are moving more and more to the right. However, we're not seeing that only for the positive things. We're seeing that unilaterally. We're seeing that across the entire data set. So we do want to apply more downward pressure, which could imply creating more negative hinters and that sort of thing. So that's what we're going to do. We're going to take the negative hinters we defined earlier, and we're going to run them. And then we're going to see what that does to our hand label charts here, our confusion index. And we can see that it does make some difference. However, we still have a crazy, crazy bar, like very near 60%. We can still see that that exists here in the rest of the data set. And if we actually calculate the probability or the precision recall and F-score, we're at like, 67% precision, recalls at 72%, F-scores at 68. So like, fine, we're doing aggressively okay at this particular task. Again, we haven't spent all that much time creating heuristics. We sort of picked the lowest hanging fruits. You could imagine that we could just keep going through this process and we would eventually get good results, but it's requiring a fair amount of thought. We have to come up with these terms. We have to say, okay, if we see the term anesthesia, then it very, very likely indicates surgery. Or if we see the term blade, it very likely indicates surgery, and so on. You can imagine that like after you pick the lowest hanging fruits, it becomes less and less obvious what your next set of heuristics should be. And this is part of the problem, frankly, with weak supervision alone. A lot of the time, your heuristics are not going to be obvious. They're not going to be the most obvious things that you can pick from the lowest branches of the tree. Oftentimes the most interesting heuristics are ones that are less obvious and the ones that sort of like align on some set of fuzzy boundaries on your classes. So what we can do is we can actually generate some weak signal automatically. And there are an almost infinite number of ways to go about doing this. I'm just going to show you one of the most obvious ways for this data set, which is using some very simple clustering. So in our case, we're going to use TF-IDF and k-means. Now, if you're not familiar with these particular techniques, they're pretty common, at least in the world of NLP. TF-IDF just means term frequency inverse document frequency. It just indicates like terms that represent particular types of documents. It's a very well-known technique. You simply take the frequency of a term and you multiply it by the number of times it shows up in a document, or actually the inverse of that. And that gives you kind of like an importance score for a set of terms. So we're just going to pre-process the text really quickly. We're going to, remove numbers, remove stop words. We're going to transform everything to lowercase so that we don't get any like weird alignment issues. So we wrote a simple function to do that. And I'm not going to run this because it's going to take a second to run, but basically we're going to apply this function to the entire data set. But in our case, we can say we already did that. And then we're going to initialize. Oh, actually, just kidding. I do have to run this. I forgot that I overrode these earlier in the notebook. So while that's running, I'll sort of explain what else we're going to be doing here. So once we actually clean this data set, the next thing that we're going to be doing is vectorizing it. So vectorization is simply the process of turning text data into essentially numerical representations that still hopefully hold a lot of the same meaning. And this is what models obviously use to predict. As I'm sure everyone here knows, models don't often work directly on text values. So you actually have to turn it into something that's useful for it. So this is one of an almost infinite number of ways that you could go about vectorizing. So we're just, once again, picking like the absolute lowest hanging fruits. Now, once we vectorize, we actually fit it to a model. And then later on, we're actually going to cluster. And the interesting bit about clustering is that it's a completely unsupervised technique. So we don't actually require any labels for this. And we have several different hyperparameters we could play with. So for instance, here, we're just going to choose 3 centroids for no other reason than it's a small number and it's easy to reason about. But you could imagine that we could rerun the same process with 4 centroids or 5 centroids or however many other we'd like, and we might see additional information, things that are potentially useful. So we're at least going to start with 3 and kind of see how we do from there. And out of these clusters, what we're going to do is we're going to look for relevant keywords. So we're actually going to show the most useful keywords, so the things that rank the highest. So we're going to get, the 50 top keywords, let's say. And we're going to take a look as sort of like quote unquote subject matter experts, which I certainly am not in the world of the medical field, but we're going to pretend at least for this. We're going to go through and we're going to see, okay, of the words that we see here, which ones seem to be predictive of surgery. And it's a relatively straightforward process. And then from those keywords, we're going to hopefully use some of them to create new hinters. And we're going to see what that does to our label distribution. So in this case, as the user, as the SME, as the domain expert, we didn't have to manually come up with a bunch of new hinters. Ideally, we can use sort of an automated system to give us inspiration, and then we're reacting to potential heuristics that we could create. We can manually say, okay, well, out of these words, these are the ones that are most predictive of surgery, and these are the ones that are not. We could sit here and react. But coming up with these on the fly, coming up with these from absolutely nothing, is obviously more mentally taxing. So that's sort of the reasoning behind running this clustering ahead of time. What we're doing is we're producing signal that the subject matter expert can just react to, and we can pick and choose from that pile. So let me see, are we done here yet? No, it's still going to take a while. I'm running this on my MacBook Pro, so this data set's reasonably large. It might take a second. In the meantime, are there any other questions? Let me take a look. Nope. Looks like things have been relatively clear so far. Okay, well, we're going to keep letting that run. It should only take a couple minutes more. So another interesting thing here is, again, we happen to be doing clustering, but there are like several different techniques that you could apply here. You could go as far, like in our product, we actually do things like we run like Monte Carlo simulations instead of just like simply clustering. Um, we do like several different things. The other interesting bit is that your heuristics don't have to be as simple as just like keywords that we're doing here. We're, again, picking the lowest possible hanging fruits. Your heuristics could, as I mentioned earlier, be even other labels. They could be model inference. So you could have a model that was trained on a similar problem that you might want to see like, okay, if that model says that this is class X, then it's very likely class X. Or alternatively, it might say it's class A, but class A is similar to class X. So we might want to weight it down a little bit, but still use it as a heuristic. There are lots of like very interesting things that you could do here. And the whole benefit of weak supervision is you're not looking for perfection in these heuristics. Strictly speaking, it just needs to be better than random at predicting a particular class. And that's really all that matters. Oh, we do actually have a couple questions. Would you consider using a transformer model for clustering? Absolutely. This is yet another example of just like more intelligence could potentially yield something more interesting. So totally. I think another interesting question to be asked is, what are your requirements for explainability through this system? Obviously, you could make your heuristics arbitrarily powerful. You could make your heuristics like, you could have BERT as one of your heuristics, or like some inference from BERT. You could have another be like CLIP or something else. You could have several different like large transformer models as your heuristics. But obviously, you then lose some of the ability to explain why a label is the way it is. And that could be like bad depending on your use case, or you could be okay with it because those transformer models are actually providing a ton of value. So it just comes down to like your use case and how important explainability is in sort of like your downstream processes. But there's nothing like technically preventing you from running a transformer model. In fact, it might actually perform quite well. Can we talk more about the Monte Carlo simulation? Yeah. This might be a little product specific, and I wanted to focus this talk more on like the fundamentals of weak supervision and so on. But since we have time to kill here, yeah. So just a quick plug, I guess. As was mentioned earlier, I'm the CEO and co-founder of a company called Watchful, and what we do is we build software that helps automatically label data for machine learning. And weak supervision is one of the tools that we have in our toolbox in our product. We also do things like active learning, and we have these like Monte Carlo simulations and several other like statistical things that happen under the hood. Again, our belief is that there is no one size fits all solution to solving all labeling problems. So we have to kind of like be clever about how these all combine into a single workflow. But with the Monte Carlo simulation, our product is kind of unique because we did what people typically tell you not to do, which is we invented our own query language. So instead of having to like go through and write like pandas type queries where it's like, okay, if in this particular column, if it contains surgery, then we do all these other things. Instead of like requiring our users to know this entire syntax, instead we have like a very simple, very low code way to express these types of things. And it goes way deeper than that. Like you can do Boolean combinations, like you can do things that would ordinarily take like 20 to 50 lines of Python code, and you can do it in a single line of our label query language. But the beauty of all of this is that we own the entire grammar space. We own the entire space in which you're able to create these queries. And the side effect is, since we own that, and because we've specifically made it really small, we can simulate it. So in our Monte Carlo simulation, we're actually simulating all possible queries that the user might want to create based on the queries they've already run, based on the things that they've created as hinters, based on the hand labels, based on several different sources of information. We can also suggest to the user that they hand label specific rows so that we get additional signal about specific like heuristics that are maybe like kind of quote unquote staged in the simulation, but not yet committed. So we want like a little bit more information. And we do a lot of like really clever things around like speed of tokenization, speed of querying, speed of indexing, and that sort of thing. So like we're able to run these queries at the level of like sometimes nanoseconds, kind of regardless of your data set size, because we own the entire space within which we're simulating. So as a result, we can simulate lots and lots and lots of like large sets of like very nice queries in a very short amount of time, and we can suggest to the user very sophisticated queries that might actually be useful heuristics. So that's kind of how we use Monte Carlo simulation, or at least one of the aspects of it. Next question by David. You don't use the conversion to base form sliced to slice. I mean, so for context, I kind of like threw this together. So like there's a lot of room for improvement in the code here. If you have some suggestions, you'll get the notebook after this. Please open a PR. I would love for other people to contribute to this. That would be awesome. But yeah, you'll see some like unconventional things in this notebook simply because I just threw it together for the sake of demonstration. Okay, Mia, do you use bootstrapping? Mia, maybe if you can explain a little bit more about what you mean by bootstrapping in this case. I think the answer is probably yes, but I'd want to learn a little bit more about what you mean by bootstrapping here. Okay, Yuri asked, how does your company's product differ from other open source libraries like Snorkel? This is a very good question. So there are a couple ways. Snorkel you can think of as basically everything up until this point, up until like weak signal generation. They provide obviously like the label model, they provide the mechanisms for which you can create labeling functions and so on. There are a couple like key points there though. Let's say that your users are not data scientists or they're not familiar with Python syntax. Suddenly like using Snorkel open source might be a little bit cumbersome. It would require data scientists to translate their experience into like Python functions that are actually useful. And that might be okay, but Snorkel doesn't really help you in discovering new types of heuristics, new types of labeling functions. It also doesn't really do very much in the way of telling you like how good your heuristics are. You would look at like overlap and conflict and those types of metrics, but like even then, even for like a weak supervision expert, it's very difficult to just look at those metrics in a vacuum and be like, oh, that's clearly a good labeling function, or it's clearly not. So that's sort of like point number one. Snorkel is like all in weak supervision. And again, as I mentioned, our conviction is that there is no one size fits all machine learning technique to solve all labeling problems. So what we do is we use weak supervision in conjunction with several other machine learning techniques like active learning, and we also combine it with statistical techniques like as I mentioned, like that Monte Carlo simulation and several like Bayesian techniques and that sort of thing. Because what we discovered is a workflow that combines all those different parts tends to perform better. So overall, you should see like a way faster workflow using our product. B, we're not all in on this like one like machine learning technique, and C, you can bring different people to the table and they can use the product directly. So you can have subject matter experts use Watchful directly because it's like largely point and click. You could have data scientists use Watchful directly because we have this like really nice query language. So you can slice and dice through your data in like very specific ways, and it's like incremental. So we basically like make the whole experience just like way nicer than having to cobble it together yourself. That's sort of the whole point. Anyway, I just noticed that it's finally finished running. So let's go ahead and run the vectorizer. I'm going to speed through these parts of this. So we're going to just run k-means with 3 clusters here. We're going to visualize the clusters, get the top keywords. And here, we've got the top keywords. Let's talk a little bit about what these keywords actually show. So like cluster 0, if we look at it, it's like pressure, vital, hypertension, social, well plan. I mean, this just looks like a normal like doctor visit type of cluster. There's nothing particularly surgical about it. Cluster 1 aortic, scope, valve, anterior. I mean, a little bit more surgical, but like definitely more like cardio specific, like cardiovascular specific. Cluster 2, noted sutures, lateral, supine, dissection. God, I hope that's surgical. Anterior, fascia, hemostasis. Like this cluster is like clearly more surgical than the others. It's not perfectly surgical, but it's certainly more surgical. So what we can do is like we can just take a bunch of heuristics from this cluster, a bunch of these words from this cluster, and use them as heuristics and kind of see what happens. So first, let's just like replot the charts from earlier, just so that we have like a before and after. So these are the charts from before, and we're just gonna like re-update that list of hinters. And we only added things to the positive list, by the way. So we more or less made like the negative hinter list kind of the same. And then we're gonna run all of that and retrain our naive Bayes model. And then we visualize, okay, well, the distribution looks way better. Like if you compare this versus this, let me show some like not so obvious differences. This chart actually ends right around like 0.5, right? It's like around 50%. So the lowest probability that we actually have appears to be like just about 50%. And that's across the entire data set, which is obviously not what we're looking for. But here, it correctly goes down to 0%. And we can see a very clear right skew on the hand labeled surgery chart. You know, a lot of the things that were hand labeled surgery have a damn near 100% likelihood of being surgery. And similarly here, a lot of the things that were hand labeled not surgery have very close to 0% likelihood of being surgery. So this is looking way better. You know, we have a very, very nice separation. Now, if we take a look at our label distribution, again, we have a really, really nice separation. Giant peak close to 0%. We have like a nice other peak very close to 100%. So I'm feeling pretty good about this. Now, if we actually calculate precision, recall, etc., like we do see boosted numbers, but they're not all that much better despite having such really nice separation. So the question is, okay, why not? And so we can just query, we can say like, show me everything where like the prediction is greater than 90%. And this becomes very, very interesting. Here, we have operative note. Yet the medical specialty is urology. But this was clearly surgical because it's an operation. Pre-operative diagnosis, like obviously surgery. Ophthalmology, this literally says cataract surgery. So this is also surgery. So this is a very obvious case where, once again, like we don't necessarily have ground truth in our labels, or at least the way we were using the labels was not how the labels were intended to be used. So the side effect is we have this like skew that's introduced in the discrepancy between our data set and the way we were labeling it. So a lot of like the precision, recall, and F-score metrics that we have here are not actually representative of whether these things are truly surgery related or not, simply because this is treated as a multi-class problem, when in fact it probably should have been treated as a multi-label problem. You know, oh, sorry, my mic keeps increasing its gain. So in fact, like where we got this from Kaggle, that person probably should have treated this more like a multi-label problem, because yes, this is, you know, urology, but it's also surgery. And similarly, yes, this is ophthalmology, but it's also surgery. So if you have the class surgery here, like we really should be modeling a lot of this overlap, and it would make sense because we do have very high predicted values here. So this is just another case where ground truth is often not actually ground truth, and this is just one of the many ways that it can bite you. Anyway, just to summarize here, we went through, you know, kind of foundational weak supervision. We talked about, you know, how to reason about weakly supervised systems. We talked about, the most basic generative model that you can use in weakly supervised systems. And then we went into like generating signal for weakly supervised systems. Just know that we scratched the very tip of the iceberg here. This is like the world's fastest and simplest introduction to weak supervision. There is a lot more to learn, and there's a lot more sort of advanced techniques that you can use to generate additional signal and that sort of thing. Again, quick plug, we implement a lot of these like very advanced techniques, and we in fact invent a lot of them ourselves at Watchful. If you are interested in any of this stuff, if you're interested in data-centric AI, if you're interested in just talking more about how data should be labeled, please come visit us at watchful.io. We would love to have those conversations. Thank you all so much. And are there any other questions before we sign off here? Where can we learn more about weak supervision? Great question. So we actually have a few resources on our website. So if you go to watchful.io, go to the resources, we have several different resources there. We have things about weak supervision specifically, what you can do to train models using this probabilistic data, which we didn't touch at all here in this particular webinar. We also have some content about machine teaching, which is like an overarching umbrella over things like weak supervision. So certainly on our website. There's also a ton of papers, certainly from the Snorkel group, the Hazy Research Lab from Stanford. I will say that weak supervision is kind of a new thing. So a lot of the resources that currently exist are either like papers or largely like blog posts from basically us or Snorkel. So I would say that those are kind of like the three main places you can find additional resources. Awesome. Well, thanks again, everyone. I appreciate you bearing with me through kind of like a live, somewhat coding session. Again, you will get access to this notebook soon after this. If you have any suggestions or if you want to open any PRs, please feel free. This is kind of like a living sort of introduction to weak supervision that I want to keep going. So thanks everyone for joining us.